Okay, folks, I'm going to go ahead and start and introduce the meeting, and then Daniel, I'll go ahead and turn it over to you in just a moment. I apologize, I'm actually starting a couple minutes late, which I try not to do. So with that said, welcome to this, I guess we would call this our inaugural speaker meeting. It's a special meeting for us this week at the Boston Healthcare Technology User Group. For not only is it our first speaker meeting, but we also have our new branding package has been released, and so that's what you're seeing in the PowerPoint slide here. So my name's Paul Swider, and I'm just going to kick off the meeting and let you know about sort of who we are and what our mission is. So in short, we're the Boston Healthcare User Group based out of Boston with a global reach. And our mission is to bring global top-notch speakers to share 30-minute, quick lunch and learn topics, if you will. And so we're really excited to grow the community. We have links for our mailing list and for our Discord server, and these are on the PowerPoint slides with the QR code, and they'll be available after the meeting. So that's funny. Nice. So with that said, I will turn it over to Tomas and Daniel. I'm really excited as a data person, and it looks like they have a funny sense of humor like me as well. As a data person, I'm really excited to listen to what these folks have to say, and especially as fellow Discord community members. So it's one of the things that's new to me, but not new to these folks, is the Discord community, and that's how we met. And so I was really excited that they were able to speak today. And so with that said, I'm going to go ahead and make you a presenter, and I'll let you go ahead and take over the show here. Let me see.
Thank you.
All right, sorry about that. Give me a minute here. I'm not quite sure why. There we go. You would think this was my first Zoom meeting. Okay, there you go. You should be all set. Thanks.
Yeah, 1 second. Can you see my? Can you see our screen?
I can see it very well. Thank you.
Excellent. Good. So So welcome everyone, and thank you for having us today. I wasn't the one, I wasn't aware this was the inaugural meeting, so I feel privileged and quite a bit of pressure to hopefully deliver something interesting to the community. So thank you for having us today. My name is Tomas, and also thank you to my colleague Daniel, who set this up in the first place. He's walking just behind the camera right now. So just a couple of things about us. Now, my name is Tomas. This presentation is actually co-developed with one of our community members who works at Roche, Conrad, and he won't be presenting today. You will be able to listen to him at our conference next week, but I'll say a few words on that in a second. But here we're going to look at disease research aided with a knowledge graph, and specifically looking at an open source project that we worked on where we integrated a bunch of biomedical data sets into one Kraken knowledge graph. And so this talk will be technical. We're going to look at some code, and hopefully it'll spark your interest to explore and learn more. Like I said, it's open source. You can go to GitHub and check it out. But first, we are, as you mentioned, we're also Discord members. We've been on Discord actually over a year. Our Kraken community of developers building applications, building software is on there, and you can find us there. If you go to kraken.ai/discord, you'll be able to find our community right there. And also, if you want to learn more about Kraken, you can find ours also on YouTube. We do a bunch of a lot of these types of events. Online, of course, because of the pandemic, and I very much welcome if you want to again learn more about Kraken, do check that out. And like I said, we have our conference next week in just under 7 days. We'll be live streaming. We have, I think, close to 30 sessions panels and presenters from life sciences to robotics to all sorts of different things. So have a look at our conference, which is in just under a week's time. It's called Graken Orbit. But we're here to talk about a knowledge graph in disease research aided by a knowledge graph, and with a specific focus here on COVID-19. So like I said, this repository is open source. You can check it out on the link right here in our repository, Graken/biograken-COVID. And what we're going to look at, and we won't have time to dive into the details, and I'm happy to leave a few minutes at the end for questions. But we want to explore how we went about building this. Now, if you're unfamiliar with Graken, Graken is a database, and I'll leave you to watch some other videos if you want a more in-depth conversation, but it's particularly a game changer if you're working with complex data. So we're going to look at specifically some of the modeling decisions that we made and how we use Graken to model the data relevant to building this knowledge graph. And that starts first with choosing the right data sets. And then we're also going to look at some of the medical papers that we ingested. And finally, there's some example queries that we can run. And again, do check it out on your own if you go to the repository online. Because of time, we won't be doing a demo here, but check out online. There's some cool videos there as well. So let's look first at the data sets that we have available. And especially in biology, it's some of the usual suspects that I think some of you are familiar with, from UniProt, Ensemble, TissueNet. Those are the ones that we put in Graken. There's just under a dozen or so that we put in, and as we'll see in the latter part of this presentation, we also looked at SEMmet, and we pushed a subset of SEMmet into Graken as well. And what data does this relate to? Relates to proteins, relates to tissues, relates to genes, transcripts, pathways, diseases, drugs, organisms, viruses, tissues, and medical papers. But as what's always important to keep in mind when we think of building these types of technologies is that if the source data needs to be right, because if you put in garbage, well, you get garbage out. And so it's important that we first have the right data, and then once we have that right data, we model the real world in as exactly the same way as how we perceive reality. And that's where Graken is really useful for. So how did we go about modeling this knowledge graph? And to be very, very practical, let's look at an example here. So here we've got a table. If we're using something like UniProt, we may export some data in a CSV file in a tabular format, and we may have some column names that look like this: UniProt ID, UniProt name, protein name, function description, gene symbol, UNTRUST ID, ensemble transcript, and organism. And so how do we go about modeling this in Graken? If you're unfamiliar with Graken's type system, Graken implements a very, very high level, very expressive type system. Specifically, it implements directly the implementation of the entity relationship model directly at the database level. So rather than thinking in tables, i.e. enforcing some sort of tabular structure in our database, we actually want to model things in a more natural way in terms of thinking what are our entities, relations, our attributes. So for this example here, we would say, well, we've got 4 different entities. We have a protein, we have a gene, we have a transcript, and we've got an organism. And we want to model this in such a way that we can connect all of them together. And to do so, we want to think, what are the attributes that connect to each other? Because first, there's a bunch of attributes, or either the columns that relate to this different entity. And then we want to model those as attributes. So in terms of nomenclature, an entity here is denoted by a rectangle shape, whereas an attribute's denoted as a circle. So here we see that we've got, for example, at the right, we've got an entity organism that we want to say that it has an attribute of type name. And we'll do the same for the other attributes as well. But then we want to link them with each other as well. And the way to do that, or the way we chose to do it in this model, is by creating 3 different relations. to model proteins, genes, and transcripts. We say that between a gene and a transcript, we have a transcription relation. We say between a transcript and a protein, we have a translation relation. And between a gene and a protein, we've got a gene-protein encoding relation. And what's really important in that the practice that Graken tries to establish for you is that when you're working with data that has a lot of different types of relations, that the naming is chosen very carefully so that later when you're making queries that can be quite complex, the querying actually is heavily simplified. And to model this in the Graken language would look like this. So we first use the keyword sub to declare that this entity is called protein. And we do that by saying protein sub entity. There's 4 different attributes that we say this type can have. There's the protein owns an uniprot ID and 3 more attributes as well. And then we've got the concept of a role. And this is where it starts to become very expressive in how we start to model our data. Because the role effectively establishes on how the context in how a certain thing plays a role in a relation. So in the case of a protein, we say that there are 2 roles that they play. There is a translated protein and there's an encoded protein that relates to the protein entity. And but before that we say that we scope them to one specific relation, specifically the translation, because the role translated protein shouldn't be allowed to be played in any other relation. So we use the keyword place to effectively make that restriction. We do the same for a gene. So here we've got another entity that has 2 attribute types, a gene symbol and an address ID. A gene also plays 2 different roles, an encoding gene and a transcribing gene that are scoped to their respective relations. And finally, we've got a transcript that has just one attribute and is also scoped to 2 different roles. And then we start to declare the relations that we have. And the first one is this gene protein encoding. And as you can see, we also use again the keyword sub to denote that a gene protein, that label corresponds to the type relation. And then we say that there are 2 roles that relate to that relation. So with the keyword relates, we now can scope and can restrict that only those 2 relations that are mentioned here are actually allowed to be played in that particular relation by whichever thing has those roles using the keyword place. We do the same for the other 2 relations that we have, translation and transcription relation. And so what you're looking at here right now, this is a big chunk of how we would go about modeling in Graken. Most of the Graken schema consists of these keywords like sub, owns, has. We try to keep them as small as possible so that it's first easy to learn, but it's also highly expressive and simple when we're trying to model what can become very complex models just by their background. Now for BioGraken COVID, which is the name of the repository, there's the main entities, there's more, but the main entities are the ones that we see here. So we've got proteins, transcripts, and genes, as we mentioned. And then we've got a bunch of other types, pathways, viruses, tissues, drugs, diseases. And that is helpful, but we also looked at papers. So the model is also extended by looking at papers. And so we've got journals that connect the papers that have authors which are part of organizations. And then we've got, and to model that, we also build that in the schema, which effectively looks like this. We declare journal as an entity like this. We've got a publication that is also an entity with 2 different attributes and plays 2 different roles. There's also a person as an entity type. There's an organization as an entity type. And then something that we haven't seen yet is that we can also create subtypes. So an organization is a great entity type, but sometimes we may have subtypes of organizations, such as laboratories, institutions, or companies, where we want to say that every organization is always a company, but not all companies are organizations. And we do that, again, simply by using the keyword sub. And so this way we can create a hierarchy of things. Think very much like object-oriented programming by using inheritance. That's effectively what we're doing here with the entities and the type hierarchies, as we call them. We've got a relation that we call an authorship relation that relates to two different roles. We do the same for affiliateship relation, which is how, as we see, is a person connected to an organization. And finally, the publishing relation, which effectively the person publishes in a paper. Now, what's clear now is that while we may have the schema, we haven't yet connected papers with the biomedical domain. So now there's a couple of ways around of doing this, but to start off with, we created a very simple relation called a mentioned relation. We said that given some source data that we have, we want to say that certain biomedical components have been mentioned in certain papers. And we do that by using a simple relation that we decided to call mention, that has three different attributes: a start position in the text, an end position in the text, a source of the actual text, and then it relates to either the mentioning paper or the mentioned biomedical component. So, for example, protein ACE3 has been mentioned in this paper. And so that's a good segue to look at how we actually went about ingesting some medical papers. Now, it's important to mention Kraken doesn't do the NLP. So Kraken is a database, and as such, it'll ingest whatever structured data that you give it. And what we looked at was actually at how can we push papers through some NLP algorithm into Kraken. And one of the ones that we looked at was this NER that was done over some of the court papers that were released last year. And this is a good data set because first it is open source and it uses UMLS as its ontology to do the training and then the labeling. And so we looked at that data, and effectively what you get are these big JSONs with different IDs, source, authors, and a very simplified version of a JSON looks like this, where in the entities part, that's where all the different entities that have been identified are listed, and the rest is sort of metadata. So you see that there's a start position, there's an end position. The type denotes to where it's been identified based on UMLS. So it uses, again, UMLS as its ontology. That's why disease or syndrome, which is according to the UMLS terminology. And then the text, which is the FPV infection. Now, of course, it's not perfect, and sometimes I think Hong Kong has been identified as gene or genome, but it's interesting enough to have a look. And so we started first by ingesting the authors. The data has not been pre-processed in the most beautiful way, so there's a bunch of pre-processing that we do. We insert the journals, the title of the abstract, and then we've got the entities at the bottom, which is the most interesting part, really, what we're trying to link, which is what papers are mentioning what genes, for example. And so what we do here is the ontology. We say, okay, this disease or syndrome, we match that to the entity disease with the value of, in terms of name, FPV infection. There's a bunch of persons listed as authors. There's a publication, which we connect using an authorship and an author to authorships relation. There's a publishing relation, as in this publication has been published in this journal. And finally, there's the relation between the publication and that entity disease with that value. And on that relation, we add two attributes: the start position and the end position of where that specific entity was mentioned. But having just a mentioned relation is really not that useful, because now we can have a bunch of number of, if one paper mentions any type of biomedical components, you would get that in the data. So you could potentially do something like co-occurrence, scores, but on the whole, it's not very semantically interesting. So that's where SEMMET becomes quite interesting, because SEMMET is also available on open source, and we can. This is basically the main schema that you find in SEMMET. There's a bunch of tables. SEMMET on the whole is effectively a lot of triples that were ingested after some NLP from PubMed. It's a very large repository and very, very interesting to do big data analytics over, and also pushing it into Kraken. So here we see there's an entity table, there's a predication table, and there's a sentence table that are of particular interest that we look to ingest. So this is the SQL query that we took, because the data is offered as SQL as well as other formats. And then this is the result that we would get. So we've got triples that we're looking to ingest with a subject and a predicate and an object that we're pushing in. So let's say we've got this triple here, where we say that NDUFS8 interacts with NDUFS7. Now that's started to become really interesting, because now we're ingesting actual data from the NLP in a structured way into the database. Because what we do now is that we simply say that there's an interaction relation between those two entities. And we also then map, we say we've got a mapper also in the loader that says that if you find the triple or the predicate called interacts with, we want to map it to our schema where there's a relation that's called interaction, where the passive role and the active role have been assigned by the schema, interacted and interacting, which is what is according to the schema itself. And so this allows us to, in a very, very automated way, ingest all of the data from SEMMET into Kraken, or specifically a subsegment here that is of interest to COVID-19 research. So what's this doing is basically saying that the interacts with is mapped to the predicate, and then the active role is basically the subject, and the passive role is the object, which we then map to the relation itself, which here says, as we saw before, that this particular NDUFS8 plays the role of interacting in an interaction relation, where NDUFS7 plays the role of interacted. And then, as we get to the end of this presentation, there's some very interesting queries that we can run. For example, return a gene that stimulates another gene where the stimulated gene has an association to SARS. Also, return the publication that mentions that stimulation, and finally, return the drug that the stimulating gene is inhibited by. So those are the types of quite complex queries, but are very interesting to look at for scientists as we go about doing our research. I won't get into the details of the query, but I hope it should be fairly self-explanatory as we explore the ways of modeling. And then this will be the results, the visual results, if we use Workbase, where we can effectively model things in the right way. And then the final query that we can do here that I want to show before we wrap up, let's say we want to return a virus that is associated to a gene, all papers that mention that gene, and where that gene is stimulating or stimulated by another gene, and where that other gene stimulates or is stimulated by yet another gene, and where that other gene is connected to a virus. Again, a very interesting query, but fairly complex to do if you were not using Kraken. And yes, there's more to the query. We also want to know the publications where those stimulations have been mentioned. And then the visual results could be like this. Here we've got a gene, JUN, that's connected to TNF, that's connected to PARP1, that is connected to the virus name IBV. And so this is where it gets really interesting. There's a lot more that we can do on BioGreg and COVID. I want to look at that today, but I think we're out of time. So thank you very much for having us. And I think I'll wrap up. I'll leave it there. Yes, thank you.
Great, thank you. That was really amazing. I'd like to, I do have just a quick question as we're wrapping up. Do you do you picture yourself more on the research side where you're providing, you know, this sophisticated language for these for researchers to use this knowledge base, if you will, to query the data, or do you, and you know, do you disseminate that information as well for reporting purposes? So, you know, based on the demo I saw you do, it looked like it was might be more intended for the researcher. But then on your roadmap, I saw real quickly something about you know, data sets, which would imply that you would be able to connect, you know, a visualization tier to it, and maybe disseminate some of these you know, queries or reports. So yeah, sorry if that was a long question, and I know you only have a minute. So go ahead.
No, it's fine. I mean, just to be clear, Kraken is a general purpose database. So this is just one example of how we can use it. Of course, this is more on the R&D side if we're doing drug discovery where we need to ask these complex queries. So yes, this is more on the R&D side. But of course, if you want to build on top of Kraken a visualization software to visualize this that has your GUI, then go ahead. Again, Kraken is a database, just like MySQL or Postgres is a database. Kraken is used for things like robotics, for cybersecurity, for basic chatbots. So there's a lot of ways on how you can use it. The key is that the language and the type system allows you to in a very simple way model the data and then ask very simple questions, and also reason over the data, which is something we haven't actually touched on today. So the example is really more on the R&D side. By the way, we use Kraken, certainly not. And this whole project is also just, again, an application of Kraken, which is open source. But Kraken itself, like I said, is a database that is your canvas to do whatever you want to do with it.
Yeah, no, that's great. And thank you for that explanation. It's brilliant. So I would love to send an offer for you folks to return, you know, in a few weeks, and maybe we can do a part 2 to look at, you know, how we would piggyback on top of this. So I do realize it's a short meeting, but we're doing that on purpose. You know, I think people are a little overwhelmed with online stuff right now. So we want to keep things live and short, and that's it.
Yes, and thank you for the others for joining as well.
Yeah, absolutely. So with that said, everybody, thank you for attending, and I'll follow up so that you can have access to the slides, and we'll see you next week. So thank you.
Great. Thanks so much. And I hope to see some of you at the Orbit as well.
Yes.
Take care. Bye-bye.